All right, well, I'm going to go ahead and start up. We have essentially covered Maxwell's equations. I've hinted a little bit at some of them, and there's some issues with one of them that still one makes it not quite the symmetric system that you have, that you would expect to have in our universe, because it turns out just about, well, I should say at least a lot of times when we expect asymmetry to exist, whether it be a particular graph. There's a case in history where we had pretty much a dot, a dot, a dot, a dot, and a dot. And based on that particular graph and the fact that this little dot that needs to be right there wasn't there, some people predicted the existence of a particle, and from that they ended up Murray Gell-Mann won a Nobel Prize, partly based on the idea that there's no way that the universe would exist with such a lack of symmetry in a graph. So it turns out that that's a lot about physics. And when you hear Brian Greene talk about the elegant universe, and people say, you know, physics is elegant or beautiful, that's really what they're referring to. There's a lot of symmetries that exist. And there's two potentially lacking symmetries. One's really minor, so we don't think much about that, and that's what I'll cover first. And then the other one's kind of a big deal and actually led to a discovery. So let's go ahead and get started. I'm going to start off by sharing my screen and then allowing you to see the equations that we've covered to date. I don't know why it's not coming up right now, but now it is. Okay. So I'm going to share the screen. Feel free to ask me any questions. I did take questions at the beginning, but before the class actually started, a couple of people asked questions, but that was about it. So if you have one, you can stop me before I get on the roll here. All right, so we had Gauss's law, and I'll show you later that Gauss's law can be written in differential form, which is kind of nice as well. But not only is Gauss's law a thing, we know the closed integral of E dot dA is equal to Q enclosed over epsilon naught. I'm leaving off the enclosed part just because it's obvious now that we've had enough experience with it, and it just is cumbersome to write. Well, it turns out vector calculus teaches us that basically you can compute a vector field up to an additive constant, meaning you could have a vector that has constant components, X, Y, and Z components, for instance, that could be added to it, and it'd still be quote unquote the same vector field. But it only takes to get up to that constant, that additive constant of a vector field, it only takes knowledge of something we call the curl and something we call the divergence of an electric field. So it turns out these Maxwell's equations are four equations, basically four equations, two of which are for the curl and divergence of the electric field, and two of which are for the curl and divergence of the magnetic field. And this Gauss's law is in fact related to that divergence. So it turns out there's an equivalent one, and we've alluded to this earlier in the semester, but there's an equivalent one for the magnetic field. Only, as you've seen throughout the semester, it turns out that when you go to draw electric field lines, you sort of draw them as if they originate on a positive charge, and then they terminate on a negative charge. That is the characteristic of a divergence full electric field, or any vector field for that matter. It would have a source and a sink, and in the case of the source, it's a positive charge, which is why there's a Q that has the ability to be positive for a source, or the ability to be negative for a sink, over some constant. That's why that's on the right hand side. So that means that electric field lines can actually radiate outward and look like they're diverging from a point, and they can in fact converge inward and look like they're converging to a point. They would converge to a negative charge, and they would diverge from a positive charge. Well, it turns out magnetic field lines, all the ones that we see in nature, are either transitory, meaning they're getting ready to die out, and that's why they're broken, or they're complete loops. So for instance, if you looked at a bar magnet, you've seen that the magnetic field line exits the north end of the bar magnet and then loops back around and enters the south end of the bar magnet. Well, it turns out if you were able to, you'd see that that magnetic field line goes all the way through the bar magnet and then makes a complete loop. And in fact, that's the norm, is that there are complete loops. And if we actually had the ability to say, take a bar magnet and cut it in half and then have a north pole of a magnet and a separate south pole of a magnet, then we'd expect this left-hand side of the equivalent of Gauss's law for magnetic fields, we'd expect that to be equal to something other than zero. But it turns out, in fact, that it has to be equal to zero. And that's basically evidence that there are no magnetic monopoles. That's what we call it. You can also look at it as basically Gauss's law for magnetism. And it does introduce a little bit of asymmetry, but it's not really the kind of asymmetry that we're bothered with. When we're talking about symmetries with differential equations, we generally care about symmetries with regards to derivatives of functions, not just scalars. So for instance, the equation for the harmonic oscillator can be a second order differential equation. It can be homogeneous, so it's equal to zero, or it can be non-homogeneous, which will have it equal to some constant. We don't make much of a big difference between those two. So the same thing here, that one's not much of a big difference. And it turns out physically, we just don't have any ability to do anything other than put a zero there, because there just appears to be no such thing as a magnetic monopole. I literally was not yawning until this class started. I don't know why. All right. So now the other equation, of course, that we know of is Faraday's law, and then the other one is Ampere's law. So Faraday's law basically says we're used to writing the induced EMF, that fancy script E. The induced EMF is equal to negative. Maybe we put a capital N in there, and then d phi dt, where phi is the flux of the magnetic field. I'm going to write it a little differently by making note of the fact that in a closed circuit, in order for you to have an induced EMF, you actually have to have an electric field that in some sense pushes the magnet or pushes the charges around to make the current. So I'm going to write this as the closed integral of E dot dl is equal to negative d phi b over dt. Now see, that is clearly an integral on the left-hand side and clearly a derivative on the right-hand side. And in fact, if we converted this to a differential equation, we would have basically derivatives on the left-hand side and derivatives on the right-hand side. And this is where the lack of symmetry is going to come in, because when we write the equivalent equation, which is actually called Ampere's law, we get the closed integral of b dot dl is just equal to more or less like a constant again. It's just mu zero times I enclosed again. And for one, that was bothersome because we expected us to have a derivative. And in fact, from a symmetric standpoint, it looked like a changing magnetic flux, which clearly created a voltage and a current, which is due to an electric field. Why wouldn't we also have a changing electric flux creating a magnetic field? So that was a big asymmetry in nature that we just didn't expect. And in fact, Maxwell thought there was one, Faraday thought there was one. But when Maxwell was given Faraday's notebook, or was able to go through Faraday's notebook and stuff, he was able to just write down these equations essentially. But he found this one equation lacking, and this is, like I said, this is called Ampere's law. I'll go ahead and write it up here as this is Gauss's law. We can write this one as no magnetic monopoles. This is Faraday's law. And this is Ampere's law. But it's not complete. Oh, I should probably not try to put that there because it's not complete. The complete's not going to fit in. So I will erase this and say not complete. Whoa, or I'll just erase in a circle. So I know, for instance, the result. So I know that it's not complete. So I'm, sort of tipping my hand there. But either way, let's go ahead and show you what Maxwell saw. So here's the problem in a nutshell. We can imagine, for instance, a simple situation like a current carrying wire. If you have, for instance, a current carrying wire right here, then we know Ampere's law, if this is a current I, say, then we know we can do an Amperian loop where we're going to, of course, integrate this Amperian loop around so that the left-hand side of Ampere's law becomes the closed integral B dot dl is equal to, notice this one does in fact come out in front of the blue current. That's so it is consistent with the right-hand rule. The left-hand side becomes the integral of B of R theta hat dot R d theta hat, which gives us the 2 pi r times B of R. And then the right-hand side of Ampere's law gives us mu 0 I enclosed, which is just mu 0 I. So we end up getting B is equal to mu 0 I over 2 pi r, all of that acting in the theta hat direction. And that's exactly right. But the way this equation, Ampere's law, is set up with that line integral, that line integral is supposed to be true for the current going through any surface that is bounded by that Amperian loop. So closed integral B dot dl equals mu 0 I is true for any surface bounded by the Amperian loop. Okay, so what happens, and this is a key aspect here, what happens, for instance, if right here there is a parallel plate capacitor. Sorry about my cat, everybody. My wife went outside and left the cat inside, and she's not happy with the whole situation. So anyways, if instead of taking, like we sort of did here, we took the current piercing that flat surface that spans that boundary that is the Amperian loop, what if instead we considered this Amperian loop being, say, the opening hole to a Santa Claus type of bag? So we could have, in fact, sort of a shape like this. And then you see that in this case, the actual bag goes through the capacitor, but in fact, there's no current actually going through it, because in fact, it's an open circuit there. Clearly no charges can actually go through that bag. This, according to the way this equation is written, is has to be true as well, whether I do it for that sack surface or whether I do it for that black flat surface. So that's where Maxwell took off from. And what you do is you realize, okay, well, I need to have something like, oops, let's do this. So we need something like mu 0 I. And what I mean by that is we really need something that has those units. In other words, whatever the units of mu 0 are, which is Tesla meters per amp, times I, which is the amp, we need something with that unit that we can add on that other side. And we expect that it might depend on electric flux. And that's just from the symmetry of the situation. Again, we don't know that it's going to be true. We just know that magnetic flux made a magnetic field, or excuse me, made an electric field. So it seems reasonable that perhaps an electric flux would make a magnetic field. So if we start from there, we can actually consider a capacitor, specifically a parallel plate capacitor. And like we did earlier, remember earlier, we came up with these neat little equations that, actually, I shouldn't write it that way. Allie, come on, baby. Equation, which was basically the energy per unit volume was 1/2 epsilon 0 E squared. That was what we did. And we just used a parallel plate capacitor and calculated it that way. And come to find out, this is exactly the right answer, even though we did it for a parallel plate capacitor. Similarly, we did the same calculation for a solenoid, which obviously is not the general case, but lo and behold, just like in the case above, we ended up getting a result that was correct. I'm going to go let my cat out real quick just to save y'all. Hold on a second. Sorry. You go out, Allie? You go out. You go, Allie. Yeah. You go, Allie. Allie, Allie has been running my class. So. All right, I'm back. Sorry about that. So we're going to do the same thing. We're going to attack this like it's a capacitor, see what comes out, and lo and behold, I happen to know for a fact that it turns out to be exactly right. So what we know is we like something with the units of mu 0 I. So I'm just going to assume that we can put a mu 0 in front of it. That'll be fine. And then I can actually attack this as, well, let's calculate I, which is like a instantaneous rate of change of current, or excuse me, of charge. So I'm going to say I, and by the way, this term that's going to fix it is ultimately going to be something we call the displacement current. And that's a historical name that was based on a more or less a thrown away idea. So don't try to put too much thought into what they mean by displacement. Just know that that's what we've called it. So I'm going to say I displacement is equal to dq dt. And actually, I shouldn't have written that d like that. That looks really bad. So let me fix this. That just drives me crazy. Oh, much better now. Look at that. Anyways, this is just horrible. It's just getting worse. It's just getting worse. Oh, okay. So anyways, let me ignore my OCD for a second. If I could ever do that, that would be awesome. So dq dt, but remember C equals Q over V. So Q is equal to CV. So I'm going to say d by dt of C times V. And if you remember, for a parallel plate capacitor, the C is in fact epsilon 0 A over D. And then, if you remember, for a parallel plate capacitor, the voltage turned out to be the electric field times the distance of the separation between the plates. So one of the things that's nice about that is you can clearly see the D cancels out, and we can pull the epsilon 0 out in front, and we'll get epsilon 0 times D by dt of E times A, which, remember, I said we suspect that maybe it'll have something to do with flux. Well, that looks a lot like flux. The electric field times the area is in fact the flux. So if we go on the assumption that the electric field is essentially 0 outside of the parallel plate capacitor, then this E times A really is the flux. So lo and behold, that turns out to be exactly what we need. So Ampere's law with with Maxwell's correction turns out to be the closed integral of B dot dl is equal to mu 0 I plus mu 0 epsilon 0 d phi E over dt. So this is actually the correct version of Ampere's law, including the displacement current, which is the epsilon 0 times d phi dt. So anybody have any questions on that? So this is corrected Ampere's law. Now, from that, you can actually, now solve a physics problem, for instance, that has something to do with this. Specifically, what if we have a air gap capacitor? We'll say it has a circular disk for the capacitor, and we'll charge it up to 70 volts, say, and put it in line with a certain resistor, and then calculate some stuff. So let's actually apply this. So here's an example. So what we're going to do is we're going to imagine that we have a capacitor whose capacitance C is 50.0 picofarads. Its area A is going to be 100 square centimeters, which isn't that helpful to us, of course. We're going to say its voltage that we raise it to, which we could call, say, V0 if we wanted. I said I would use 70. I think I'm going to use 100 instead. Okay. And I'm going to say we put that in series with the resistor R, whose resistance is 4.00 ohms. And what we want to do is connect the battery and attempt to charge up the capacitor, in other words. And then at t equals 0, the electric field is going to start to crank up. And in fact, it's going to change most drastically at that t equals 0. And at that instant, what we want to do is calculate the current in the RC circuit. And we want to determine the rate of change of the electric field between the plates. We want to determine the magnetic field induced between the plates. And we're going to determine B beyond the edge of the plate. So we're going to determine A at t equals 0. At t equals 0, we want to know the current. And I'm going to draw a picture in a second, so that'll help us out a little bit. Part B, we want to know the rate of change at t equals 0. So we want to know dE dt at t equals 0. And C, we want to determine the magnetic field induced. And then D, what we'd like to know is determine B everywhere. In other words, not just between the plates. Okay, so our system looks like this. Basically, we're going to have a 100-volt battery running to a switch, running to a resistor, running to a capacitor, and then back to the actual battery. That's what we're shooting for here. What we do recall, hopefully, so I'm going to start here with solution. What we do recall is that we solved this differential equation that we got from Kirchhoff's loop rule for this very problem earlier. And we found out that the Q as a function of time was in fact equal to C times V0 times 1 minus e to the negative t over RC. Okay. So that's actually what we're going to use. We actually know the C, we know the V0, we know the R, all that good stuff. So all that's completely calculable. What we want to do first, though, is we want to figure out what the current is. And of course, I is dq dt. So for part A, I is going to be dq dt. Now, technically speaking, we should probably put a negative in there. So no, this is fine, because I was remembering when we were after the second part, when we solved this differential equation, we allowed a charged capacitor to discharge through a wire with no battery. That was when the I was negative dq dt. So that's definitely not the case in here. If we take the derivative of Q of t with respect to time, you can see the first term, which is C times V0, is not going to give us any derivative because that's just a constant. But the second term will give us, of course, C times V0, and I'm going to put that in the numerator because I know what's going to happen. And it's got a negative, so C V0 times negative, and the negative is because the negative in front of the E. Now, of course, the derivative of e to the negative t over RC is e to the negative t over RC times the derivative of negative t to the negative t over RC, which is negative 1 over RC. So I'm going to put a plus there to take care of the negative, and I'm going to put a RC down here. And from this, we can see that this C is going to cancel out with that C. And in fact, what we have is just V0 over R times e to the negative t over RC. If we do this at t equals 0, then well, actually, I should probably break this up a little bit. I'm going to do that. I'm trying to fit too much in that little space, and that's probably not good. So I'm going to say at t equals 0, I of 0 is equal to V0 over R times e to the 0, which is just V0 over R, which obviously is 100.0 volts divided by 4.00 ohms, which is 25.0 amps. So that's our first answer. 25.0 amps. Anybody have a question with that regarding that? So this is amps, and it's coulombs per second, but really what it is the amount of charge that is accumulating on one of the parallel plates, say, every second. Now, obviously, if you remember what this graph looked like when we actually did this analysis of closing a switch like this, we saw that the current ramped up really quickly, but then it gradually tried to slow down, and actually asymptotically approached V0 over R. So that's what we're really shooting for here, is realizing that obviously the rate at which charge is delivered to the plate is actually going to decrease in time. So that's actually going to get a little smaller. If we want to know the electric field between the plates, because that's the part B, the rate of which the rate of change of the electric field between the plates, then we're going to do this part. So B, dE dt is what we really want to know, because it's I said specifically the rate of change of the electric field between the plates. So that's going to be d by dt of, now the electric field between the plates, you might recall from a parallel plate capacitor, is just sigma over epsilon naught, and sigma over epsilon naught is in fact q over a, or excuse me, sigma is q over a, and therefore we have d by dt of q over epsilon 0 a, which I think you can see is now dE dt will be actually equal to I, the current, because dq dt is going to be the current, over epsilon 0 a. So this is going to be I over epsilon 0 a, and I will just remind us that that's because this is dq dt. Now I, we already found out, was in fact 25.0 amps, and then all of that's got to be over epsilon 0, which is 8.85 times 10 to the negative 12th, and that's Coulomb squared per Newton meter squared. And then all this is times 100 square centimeters, which I'm going to choose right here to say 100 square centimeters times 100 centimeters in the bottom and 1 meter on the top, and then I'm going to square that. Obviously gives me 100 divided by 10,000, so that'd be 10 to the negative 2 square meters. So that's what the area is. So now I can finally say that dE dt is going to be 25 divided by parentheses 8.85 e to the negative 12 times 1 e to the negative 2, close parentheses, and that gives me 2.82 times 10 to the 14th. It's a really big number, 2.82, and I did have 3 sig figs, so I'm gonna, the next one would be rounded to 5, so I'm going to be forced to write 48 here. So 2.8248 times 10 to the 14th, and that turns out to be volts per meter, which is the units of the electric field, and then per second. So that is part B. Any questions on that one?
How did you get E equals the sigma over epsilon naught?
If you remember when we did Gauss's law for an infinite plane of charge sigma, we ended up making a little basically what they call a Gaussian pillbox. So it was a cylinder like a soup can that parallel to the lid and to the bottom was an infinite plane going right through the middle of the soup can. By symmetry, we expected the electric field to point straight up above the infinite plane and straight down below the infinite plane. So in fact, the dot product in the integral of E dot dA would be 0 for everywhere along the sides of the soup can label, because the electric field points this way and the DA for the soup can label would point like that. So all that disappeared. All we ended up having ultimately was the end cap, which we could call as area A, and then on the bottom, the end cap of area A. The A vector on top pointed that way, which is the same direction as the E vector pointed. And then down here, the area vector pointed down and the electric field vector pointed down as well. So that dot product just gave us EA plus EA. So the left-hand side of Gauss's law was 2EA. That was set equal to the charge enclosed, which is just sigma times A. So ultimately you got sigma over 2 epsilon naught was the electric field for an infinite plane. But then, if you remember correctly, you had a negative plane that would create an electric field pointing towards it, and then a positive plane that would create an electric field also pointing towards the negative. Each of those were responsible for a sigma over 2 epsilon naught, and they added together to give you sigma over epsilon naught total, and that's what I used. Do you recall any of that? I know it's a lot of words there. Hopefully you were tracking me. Sounds like you did though. So yeah, that's old stuff from when we first started doing capacitance, in fact. All right, so the next part, C, is where we want to determine the magnetic field induced between the plates, okay? So in this case, we're going to use sort of the symmetry of what we did with Ampere's law before. Specifically, what we had with Ampere's law was we imagined that a current was sort of going through the middle, and then tangentially around that, you could imagine a loop that whose plane was perpendicular to that current. And in fact, the tangent lines would be parallel to the magnetic field. Well, this sort of happens as well, only in this case, we got electric field lines that are pointing straight out, just like the current before. But if electric field points in a straight line, that's sort of acting just like a current, because in fact, if you stuck a positive charge on that electric field line, it would run from exactly in the same direction as the electric field, which is essentially a current. So we're looking at the end of the capacitor in a similar fashion. So that was just the world's worst circle is what I did right there, was what that was. So we're going to do it again, only I'm going to do the cheat. Okay, so with the cheating method, okay, what we're looking at is that we have a series of electric field lines that are essentially uniform. Something like this, say, and they're all coming out of the page. So what we can imagine is, since these are all coming out of the page, I'll put a dot in the center. And of course, by the right hand rule, we would want to take our right hand and stick our thumb out of the page in the same direction as the electric field. And when we do that, we would reach the conclusion that we could integrate in a circle, a concentric circle, in fact, just like that. And as long as we integrated that way, it would be consistent with the right-hand rule. So this is going to be an Amperian loop, but in a different place, or sort of in a different use at least. So with this one, we're now going to say left-hand side of Ampere's law. And the left-hand side is the closed integral of d dot dl. So again, imagine these electric field lines would compel positive charges to move in the exact same way. So in that sense, it sort of is just like a current, only we don't have a current. So the right-hand side, the mu 0 times I enclosed is just going to be 0. But the left-hand side is going to be, with our hypothesis, which remember, hopefully y'all remember, your hypothesis would be that B is equal to B of R theta hat, at least inside of there. So I'm going to get the integral of B of R times theta hat. And then, of course, the DL would be R d theta. And, of course, the R is a little radius right here, R d theta. And then that would also point in the theta hat direction. So we get the integral of RB of R d theta times theta hat dot theta hat, which I like to call is my little drunk owl. So that's going to be 1 because the magnitude of theta hat is 1. The other magnitude is also 1. And then cosine of 0 is 1. And not only that, since we're taking it on a fixed radius, R and B of R are constant. So we end up getting 2 pi R B of R for the right-hand side, because the integral of d theta from 0 to 2 pi is obviously just going to be 2 pi. Now the right-hand side of this is going to be mu 0 I enclosed plus mu 0 epsilon 0 times d by dt of A times E, which technically, you know, that's really supposed to be, I'll write it like this, but really what we're doing is d by dt of the integral of E dot dA. But the A is fixed and the electric field is uniform. So I'm just making it sort of a shortened version. Obviously, the A is not going to change. This part right here is equal to 0. So I'm going to get mu 0 epsilon 0 A times dE dt. And of course, dE dt, we can already see is I over epsilon 0 A if we really wanted to. We don't have to do it that way, but we certainly can see it already. All right. So what I'm going to do is now set the left-hand side equal to the right-hand side. Okay. And in so doing, the left-hand side is B times 2 pi R, but the right-hand side is going to be mu 0 epsilon 0, and then d by dt. Okay, I'm going back, and remember A is going to be pi times R squared, and then E is just going to be E. So the pi R squared is not going to do anything. I'm going to get mu 0 epsilon 0 times pi R squared dE dt. So we can see now that this pi is going to cancel out with that pi, and that this R is going to cancel out with that exponent of 2. And we can finally say that B is going to be equal to mu 0 epsilon 0 over 2 times R dE dt. But I'm going to put that in the theta hat direction so we'll all understand exactly what the direction is. If you remember, there was an example at the end of chapter 29, I think, might have been chapter 30, but I'm pretty sure it's 29, where we did a magnetic field that was changing in time, and it had like a north pole of a magnet was really close to a flat circular south pole of a magnet. And that, of course, created a magnetic field, and we allowed the magnetic field to change. Specifically, we assumed we knew dB dt, in other words, the derivative of the change of the magnetic field, or the derivative of the magnetic field with respect to time. And we got essentially the same result as this. So that's kind of helpful. That's part C. And I should have labeled this part C right here. So let me do that. Okay, and then part D, was we were supposed to determine B beyond the edges of the plate. Now, beyond the edges of the plate, what we know is the actual magnetic field is going to be completely determined by how much current, quote unquote, current, in this case, displacement current, is going through the capacitor whose, area is A. And in fact, there's not going to be any more out past R0, where R0 can be assumed to be the radius of the circular disk. So I might, for instance, write right here that this distance is R0. When I do that, then I can do part D. So part D, the same thing's going to happen with the left-hand side and the right-hand side and all that good stuff. But in this case, you're going to have B times 2 pi R is equal to, now you're going to have a d by dt, or actually, excuse me, let me write mu 0 epsilon 0 first. D by dt of pi R0 squared times E. Okay. Now, when you do this, you're going to see that the R's can't cancel out because they're not the same thing anymore. One's R0 and the other one's R. So ultimately, what we get for this scenario is that B, it's still going to have the same direction as the previous one, but now it's going to be mu 0 epsilon 0 R0 squared over 2R times dE dt in the theta hat direction. Notice that is, in fact, falling off as 1 over R, which is exactly what we found for it when we were treating it as a current. In other words, when we examined the part of the circuit where there was a current carrying wire as opposed to a capacitor, we got mu 0 I over 2 pi R. So this looks just like it. Specifically, it goes like 1 over R. And in fact, if you wanted to make a graph of it, the graph would be linear out to R0. That would reach its maximum magnetic field, and then it would fall like 1 over R from there on out. And that's B as a function of R. So that looks just like what we had before when we did a similar thing. The neat thing is you can actually show that this is essentially the same thing as you can show that this is essentially the same thing as mu 0 I over 2 pi R. So let me show you that real quick. We've got B, let's just take the magnitude for a second. We've got B is equal to mu 0 epsilon 0 R0 squared over 2R. And then we've got dE dt. But remember, dE dt, we calculated earlier, dE dt was I over epsilon 0 A. So we can say mu 0 epsilon 0 R0 squared over 2R times I over epsilon 0 A. Well, if you multiplied top and bottom by pi, then you'd see that pi R0 squared is in fact A. So you could say that this is going to be canceled out along with this by this guy. And then this epsilon 0 is going to be canceled out by that epsilon 0. And now we're going to get mu 0 times I on top over 2 pi R, which is exactly what we expected for a current carrying wire. Any questions on that? Oop, looks like Famato just came in. All right, so that's exactly what we got before for a current carrying wire. The magnetic field around it was mu 0 I over 2 pi r. So now we have Maxwell's equations in their correct form, and we can actually do some manipulation with them. I'll sort of quickly show you what happens. We got the closed integral of E dot dA is equal to Q over epsilon naught. Well, it turns out there's something called Gauss's theorem, which oddly enough, this is Gauss's law. So you might think that might be why we called it that. And Gauss's law basically says, hey, if you integrate a divergence, remember divergence sounds just like, let's put this as an F. That's what I'll do instead. So we'll see that this is in fact a general expression, not just one that happens to be true for E or B. So the divergence of F, which in some sense means how much is escaping, integrated over any volume, turns out to be equal to the flux that escapes the surface. Basically, all it's saying here is that, hey, if you've got a container that contains, let's say, 400,000 gallons of I don't know, jelly beans, right? If that amount of jelly beans, which is what the left-hand side of this equation is, if that's changing, then it must be going through the surface. In other words, you can't just destroy matter. And going through the surface is what flux is. So what they're basically making the argument is that obviously any divergence from a volume is equal to the flux through that surface. So now I can take the left-hand side of Gauss's law and I can say that's going to be the integral of del dot E over the volume, and that's equal to 1 over epsilon 0. And instead of writing Q, I'm going to write that as the integral of the charge per unit volume times dV. Since that volume is arbitrary, you can actually convert this to a differential equation. And that differential equation would say del dot E is equal to rho over epsilon naught. Now, in reality, if you took a electrodynamics course, you would learn essentially this, and you would study, for whole weeks, all various solutions of this differential equation. But not only that, you would also consider the case where it's not exactly electric field. So we allow for other types of fields, for instance, that occur within something other than air or vacuum. You could have an electric field like in a let's say in a bowl of wax or something, then you'd have something other than just E in there. But that's one of the things that could happen. And this is Gauss's law again. And as you suspect, as I would think you suspect, the equivalent for the magnetic field is del dot B equals 0, and you'd be exactly right there. And that's the no monopoles. Well, there turns out to be another mathematical trick that we can use. For instance, I have the closed integral of E dot dL is equal to negative d by dt of phi b. That's Faraday's law. Well, it turns out there's something called Stokes' theorem. This was Gauss's. There's also something called Stokes' theorem that basically says if you calculate the curl over a surface, then that's going to be turn out to be something that you can feel as it sort of ticks along the outside edge. And in fact, this becomes F dot dl, where dl is the boundary, the bounding line for the surface defined by summing up over the dAs. Okay, so this is Stokes' theorem. So what we can do is we can change this closed integral of E dot dl to del, oops, I should probably write in blue again, to del cross E integral dA. And then I can say, well, I still going to take a derivative, but in fact, the integral process could give me a function that's a function of other than t. So I'm going to have to change this to a partial derivative, and I'm going to replace the flux with the integral of b dot dA, which is exactly what the flux is. And now you see that we got a d by dt of a integral over an arbitrary area, and because it's arbitrary, it has to be true for any area. So the right hand side and the left hand side can be set equal to each other without the integrals at all. And in fact, we get del cross E is equal to negative partial of B with respect to t. And that's Faraday's law in differential form. You could do something similar, of course, with Ampere's law. The closed integral of b dot dl is going to be equal to mu 0. Now I'm going to write it as the integral of j dot dA, because obviously we learned a little something, plus mu 0 epsilon 0 partial with respect to t of the integral of E dot dA. Again, using using Stokes' theorem, this is going to give us that del cross B is equal to mu 0 J, the current density, plus mu 0 epsilon 0 partial of E with respect to t. And that is the differential version of Ampere's law. Your book covers this in an appendix. I'm sort of quickly, haphazardly showing you where it comes from, not going over the details of Stokes' theorem and Gauss's theorem, but this is essentially it. And now we can actually use this. In principle, you can solve differential equations by writing computer code. And there's whole courses on learning how to do that. There's books called Numerical Recipes. There's one called Numerical Recipes in C. There's numerical recipes in Fortran, numerical recipes in Pascal, all sorts of stuff like that. Those are Saul Tukolsky and some other people that wrote that book. And they're really good. But anyways, that's what you'd spend a good deal of your time doing if you were a double E, or if you worked in the field of electricity and magnetism with regards to your physics. What I'm going to do now is let you realize what Maxwell did, which was Maxwell realized once he had this equation. Yes, go ahead.
Could you go back first?
Yeah, sorry. I thought you said, could I ask you a question real quick? Now, I don't know as much about the ins and outs of double E electrical engineering. I sort of worked as an electrical engineer, but really I was more of a computer engineer working in a field where I worked with electrical engineers because basically, or computer engineers, because basically I worked in an industry that wrote software that companies like Motorola and big companies like that would actually design computers, computer processors, they would use a CAD type software and some extra software tools to design integrated circuits to make computers. And therefore, they were constantly designing op amps and transistors and diodes and stuff like that on a chip level, and we were writing the code that would help him do that. So I didn't interact that much with the actual EE engineering. I was more doing the code and actually more really just supporting customers with the code. But anyways, what I do know about electricity and magnetism is that there's probably 3 or 4 major systems of units for electricity and magnetism. And I don't know what's going on in EE regarding that, but I do know that in physics is quite complicated. The major textbook that a lot of schools use just recently, just before the man died, David Jackson, just recently switched to using the SI system, which has these units. But before that, it was the CGS system. There's also a stat Coulomb system or something. There's a SI, and then there's a Heaviside units, which were the units created by Oliver Heaviside, who really made these equations famous. He was one of those brilliant people that was able to just figure out stuff because he was friggin' a genius. And had little or no education in the field, but basically he took Maxwell's equations, wrote them in a better form, specifically inventing the vector calculus along with another guy, I think Stephen Gibbs, who was in America. Those two independently invented vector calculus. And in doing so, Oliver Heaviside made Maxwell's equations famous so that people would actually adhere to them and see how awesome they were, because poor Maxwell died at a young age from a horrible case of stomach cancer, and without a lot of the respect he deserved. A lot of people never realized how awesome he was and how many things he did right. But some of the things included, for instance, he was the first one to predict what the actual rings of Saturn were. He was one of the first people to do the statistics necessary to analyze atoms at the microscopic level. Just a lot of stuff. And he was a brilliant experimentalist in addition to a brilliant mathematician and a brilliant theorist. He did good experimental work at Cambridge as well. And he did hold the Lucasian Professor of Mathematics position, the same position held by held by Isaac Newton, later held by Dirac, also held by Stephen Hawking. And now that he's dead, a guy by the name of George Witten, I think his first name is George Witten, is in that position. So everybody get that so I can move on. All right, so Maxwell was able to put these equations together and figured out that they actually made a wave equation. And the deal with the wave equation is that a wave equation is basically always in this form. So you have the second derivative, let's say, of the electric field with respect to, let's say, Z. So that's a derivative with respect to space. That's equal to 1 over a velocity squared. And it's not necessarily going to have the symbol V there. It'll have some physical parameters there, obviously. But the main thing is we know that whatever's there is going to be the velocity of the wave squared. And then next to that is the second derivative of the same thing, but this time with respect to time. Okay, that's the form of a wave equation. And you can put, and your book does this, I might do it later because we're running out of time here. You can put Maxwell's equations into this form, and your book does it one way. I do it another way on my YouTube channel, but I'm going to ultimately do it the way your book does too. But basically, you end up getting the same thing for the magnetic field. Like that. That tells us something. And in fact, once you put it together in looking at it in the differential form, you can see a couple things. One thing that you can see really easily is that there is a wave. The wave has a velocity. The velocity turns out to be 1 over the square root of mu 0 epsilon 0. Which, if you calculate, turns out to be 299,792,458 meters per second exactly, which is the speed of light. So when Maxwell puts his equations together and forms this wave equation, he's like, oh, wow, I know what light is. So that's one of the things we discovered, was that the velocity was in fact 1 over the square root of mu 0 times epsilon 0, and that worked out to be the speed of light. The other thing that was obvious was that E was perpendicular to B, and that B was perpendicular to V, the velocity, and that E was also perpendicular to V, and all of this such that the direction of E cross B was parallel, and that means parallel not 180 degrees, but exactly parallel to V. So what does that mean? Well, let me show you with a coordinate system. So if we draw a coordinate system that goes like this, and this, and this, I'm going to say that in fact this is going to be X, this is going to be Y, and this is going to be Z. And what I'm going to tell you is that the electric field oscillates. Oops, that didn't go down far enough. Like this. Okay, so that at this point, the electric field is very strong and pointing upward. At this point, it's not quite as strong, but still pointing upward, whereas here it's pointing downward, very strong downward, downward, upward, 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 downward, downward. Now, in addition to that, the magnetic field is like this. And you can see the magnetic field. I'm actually trying to show that it's lying, oops, that it's lying in the YZ plane. Like that, okay? And in fact, that means the velocity is this direction, okay? So that's what the actual electric field is. We know certain things like there's a definition of K, which is defined to be 2 pi over lambda. There's omega, which is 2 pi times the frequency, or more similarly, omega is 2 pi over the period. So that works out nice. And in fact, in this particular case, and this is key here, you've got to be able to do this as one of the things, one of the types of problems you solve here. One, there's a simple wave equation that says the velocity, which for us is the speed of light, and that means it's the speed of light for great excess undermines various industries, Marxism rules. This is the electromagnetic spectrum. This is the backwards of Roy G. Biv. So this is Vib Gior, okay? And in fact, this end is 750 nanometers, and this end is 400 nanometers, like that. And this is gamma rays, which made the Incredible Hulk. This is X-rays, which you can look at your broken bones with. This is ultraviolet, which gives us suntans and skin cancer. Obviously, the V is visible. This I keeps your hamburgers warm and your fries. So it's infrared. This is hot pockets. So that's microwave. And this is radio. So those are the parts of the electromagnetic spectrum. And in fact, this end is high frequency, short wavelength, all the stuff you should know, high energy, and high temperature. And this is from Wien's law, which you can look up if you'd like. And this is from quantum mechanics, which says E equals HF, like that, okay? So V is equal to C is equal to frequency times wavelength. That's the simple wave equation. All of these waves, gamma rays, X-rays, ultraviolet, visible, infrared, microwaves, radio waves, those are all EM radiation, electromagnetic radiation. And they all travel at the speed of light. Of course, the speed of light does slow down when it goes through things other than air and vacuum, but they all travel at the speed of light. So you automatically know what the C is. If you're talking about FM, like 93.7, that means the frequency is 93.7 megahertz. So it's million hertz. So 93.7 times 10 to the 6. If you're talking about AM, like AM 850, which is where I used to listen to Rush Limbaugh and various other people, in this case, that frequency is 850 kilohertz. So these are all things they sort of, and I sort of expect you to know, okay? Now, the other part I expect you to know is, given a drawing like this or a description of the electromagnetic radiation, you should be able to immediately write this, which is the electric field, E. Notice that it oscillates up and down in the X direction. So for starters, I'm going to write E0 times the sine of KX, or excuse me, not KX. Notice that it's oscillating along the Z-axis. So the up and down is going in the X direction, but I have to move along the Z-axis to make it go up and down. So this is KZ minus omega T. And all of this points in the I hat direction because it oscillates up and down, which is the X direction. Similarly, the magnetic field, which we drew in red, is B is equal to B0 times the sine of KZ minus omega T. And that points in the J hat direction. And you might not realize it, but this is going in the positive direction. So both of these moving in positive Z direction. And the way you can see that is you can set KZ minus omega T equal to a constant. So for instance, if you said KZ minus omega T is equal to, say, pi over 2, then that would correspond to exactly that point right there or that point right there. Now, if you solve for Z, what you're going to get is pi over 2 plus omega T, all that divided by K. So I think you can see from that clearly as time goes up, the Z goes up. So what we're saying is this dot is therefore moving at a rate of omega over K. And in fact, it will move a distance omega k over t, or excuse me, omega over k times t in a time t. Okay, so in other words, you know now that v is also equal to omega over k. But you can see that because remember, omega is 2 pi over t, or you can think of it as 2 pi f. And then if you divide 2 pi f by 2 pi over lambda, you get lambda f. So that shows you that as well. There's one last thing I want to show you. So the main thing is right here, that E and that B that I just wrote down, that's what you get if the wave is moving in the positive Z direction. So the Z goes inside the sign, they're in phase, and it's KZ minus omega T. If it was moving in the negative direction, it would be KZ plus omega T. That moves in the negative direction. Again, negative Z direction, but if you had KX, it would be moving in the negative Y, X direction. If it was KY, it'd be moving in the negative Y direction. So that's something you got to figure out. Not only that, you've got to put the I hat with the E if that's the axis that the electric field's oscillating in. And in fact, that oscillation field, that oscillating direction is called the plane of polarization. So when you talk about polarized sunglasses, that's where that comes from. So this is the plane of polarization. So you could call it vertically polarized. Okay. Whereas the magnetic field is actually oscillating left and right, but we don't use the magnetic field to talk about polarization. We use the electric field. So that's what vertically polarized wave means, is the electric field for pulsing up and down. And remember that E cross B is parallel to V. So that introduces us to something called the Poynting vector, which was independently discovered by a guy whose last name obviously is Poynting, but also by Oliver Heaviside, and they both sent it in for publication very close to the first, to the same amount of time, to the same point in time. However, Poynting was published first, so Oliver Heaviside reneged and they named it after Poynting, but it is a vector S, and it's 1 over mu 0 times E cross B, and it is the energy, actually I should say, yeah, I'll say the energy delivered by the wave per second. So it's actually a power per square meter. So it's over an area, so per square meter. So it obviously has units, for instance, of joules per second per meter squared, which is of course the same thing as watts per square meter. It turns out that the pressure that comes from, let's say, electromagnetic radiation hitting a solar sail can be either S over C or 2S over C. So if the photons are absorbed, you get S over C. But if they are reflected, then you get 2S over C. because it takes twice as much energy to knock them back with the same velocity as they had coming in. So that's another thing the S can be used for. You'll also see that E0 over B0 is actually equal to, let me double check this now. I think this is E0 over B0. Is C. That would imply that B0 is equal to, I got to double check. It's supposed to be E0 over C. This part I know for sure. Yeah, that works. Okay. So in fact, once you find one of the magnitudes, like if you find the magnitude of the electric field, you can divide that by the speed of light, and that'll give you the magnitude of the magnetic field. And obviously the magnetic field is going to seem a lot weaker, but that's because of the units it's using. It turns out that the electric field and the magnetic field supply the same amount of energy essentially in any electromagnetic radiation. So it's more a matter of the units that we're using that make the magnetic field look so much smaller than the electric field. But all these equations are ones you should be using. You can see from your examples in your book how they're used, and it's almost always something you can just do by knowing the units. So if you just realize what the units of the Poynting vector are, if someone asks you, you know, you're using a laser to try to heat up a bowl of soup. Well, the laser is only going to land on a certain number of square meters. You can calculate how much energy it takes to heat the water up from, let's say, 20 degrees Celsius to 100 degrees Celsius. And then you can say, okay, well, this laser's giving this much energy per second per square meter, but the disk is only, you know, 2 square centimeters. So you have to account for that. But that's some of the stuff you can do. That's it, guys. We've essentially finished chapter 31. You can look at the examples. They're really, really straightforward. They're not as hard as they seem. Not only that, I might have posted some, or I'll definitely be posting some more as well. But you can look for all sorts of examples on the internet and whatnot, as well as on my YouTube channel. But everybody's free to go. I will wait for the last person to leave before I do. But I hope you all have a nice weekend, and I will see you next week. Anyone have any questions? It looks like only John's here. John, do you have a question, bud?
No, have a good weekend.
You too. Take care, bud.